Hello everyone. So in our last video lecture we have started with conformers of cyclohexane, right? In chair conformer we have studied about axial and equatorial bonds. We have studied about how to draw different chair conformers in mono substituted, di substituted or poly substituted cyclohexanes. So let's continue the topic. Chair conformers. We have seen this chair conformer of cyclohexane, this 6 carbon atoms here, which upon flipping converts into, if I am saying this as chair, then this will be called your flipped chair or inverted chair. Again, if we see, each carbon atom is having one hydrogen in axial part and one hydrogen in equatorial part. So on flipping, the hydrogen in this chair form in equatorial position will go into axial position in this inverted chair, and also in this chair form hydrogen in axial position will go into equatorial form in this inverted chair. So if we will see the stability of in these two conformers, then their stability will be same. Also if I say K equilibrium, then K equilibrium equals to 1, because concentration of this and this at equilibrium will be same because they are same, right? So let's see how to draw the Newman projection formula of this chair conformer. Actually, the Newman projection formula we have studied for entire conformers, but we started with the most stable form with the help of using Bayer's string theory, as we considered 5-member ring was most stable as per Bayer's, but in reality 6-member ring is most stable as per cyclohexane existing in chair conformation. So now let's see the Newman projection formula for this chair conformation. This was our chair conformation. If I will see here, hydrogen, hydrogen, and all the carbon atoms having hydrogen in axial and equatorial. This was your equatorial, this was your axial, right? So this is 1, 2, 3, 4, 5, 6. Now let me draw Newman projection. Dear students, I wish you must understand each and every point the way I am drawing this Newman projection of cyclic structure, because this cyclic structure may be asked in the examination that draw the Newman projection formula of either cyclohexane or mono or poly substituted cyclohexanes, right? So if I am starting here with this, you can understand this as front, this as back, this as front and this as back. I have already drawn 4 carbon atoms, right? So if I will start with now here, let's observe each and every point. If you will see this one as 1 number, this one as 1, so this back side will be your simply 2, this will be your 3, so this will be your 4, back side is 5, and this is simply 6, right? So if we will observe, this one carbon is having 2 hydrogens, one in equatorial and another in axial. So now again let's observe it properly. So this up portion, upper side, is having continuation on upper side as axial. Again here if we will see this downside, so downside is carried as axial. Again this is upside, right? This peak point is towards ups, so this upside was your axial. Again this is your downside, so your downside was axial. This point moved towards up, so this upward point was your axial. Now this point moves toward down, so this downside was axial. I have just mentioned here axial hydrogen atoms, right? So again, if I'll see here at one number, you can see this one point axial. Okay, so if we will see that front, upper and upper side or lower side, that are your, in this case, hydrogen atoms. Hydrogen atoms, these are your axial, axial, axial and axial. Okay, now if I'll see this one, hydrogen equatorial, hydrogen equatorial, hydrogen in equatorial and hydrogen in equatorial. So you can simply observe it as carbon number 1, 2, 3, 4, 5, 6. So it is having 6 carbon. This carbon is having 2 hydrogen atoms. Back carbon is having again 2 hydrogen atoms. Third is having 2 hydrogen atoms. I have not represented it here. Fourth is having 2 hydrogen atoms, one in axial, one in equatorial. Fifth is having axial, equatorial. Sixth is again having axial and equatorial. Now, what makes us to use chair conformer and not to use Newman projection formula? Let's understand limitations. Limitation of Newman projection formula of cyclohexane. So students, you can see here we have started with axial hydrogen here, axial hydrogen here, again axial hydrogen this side and axial hydrogen this side. Means for 4 carbon atoms I can easily mention the axial and equatorial bonds on each of the carbon. But if I will see carbon number 3 and carbon number 6, so here I cannot properly represent that which hydrogen will be which side and which will be said as axial and which hydrogen will be said as equatorial. So for 4 carbon it is okay, but for 3rd and 6th, means these 2 carbon atoms, it is not possible to properly mention the hydrogen atoms at equatorial and axial positions. Okay, so the limitation is 2 carbon having axial and equatorial hydrogen atoms can't be represented perfectly. So in C3 and C6 we cannot represent perfectly these 2 hydrogen atoms on each case, right? So this is the limitation. If I'll simply draw the rigid form of cyclohexane, suppose you can say this part and this part is your 3rd and 6th. Suppose this is 1, 2, 3, 4, 5. So this part, this is suppose your 1, 2 and this is your 4, 5. So this part and this part is represented perfectly, but we cannot represent this part and this part. So this makes us limit to draw Newman and better to use this chair conformer. Again, if you will observe this Newman and this chair, it is exactly same. See, this bond and this bond parallel to each other, front back. Similarly, this bond of carbon 1 and carbon 2, this front back, this bond and this bond, they both are parallel to each other. If you can say C1, C3, this bond, this one and this bond, both are parallel to each other. If you will see this bond and this bond, that is again parallel to each other. Okay, so if you will observe it perfectly, so this makes derive this chair conformer only, which is having 109 degree 28 minute. Okay, I think everyone have understood this structure. Now let me tell a few more points. Sometimes it is asked that draw the Newman projection formula of cyclohexane having some constituents. Means like you might be given that 1 methyl 2 ethyl, means simply this portion is having methyl, this portion is having ethyl. So you have to draw it here. So in that case what you have to do? Suppose this carbon is having methyl, so you can draw here in place of hydrogen methyl. Again, if this second carbon, this one is having ethyl, so you can draw here ethyl. So in that way you have to draw the Newman projection formula. Okay, so I think it's clear. Let's move to the next topic. So first of all I have to draw this one, right? This ethyl methyl. So 1 ethyl, 2 methyl cyclohexane. So if I'll start drawing, here you can take this part from front carbon or you can take this part from back carbon. It is your wish. Again, you can take this part and this part from front or back. If you are taking this part from back carbon, then you have to take this part from front carbon, or if you take this part from front carbon, then this part from back carbon. Now numbering also you can make as per your own wish. This is 1, 2. So if I'll start with this as 1, so this is having one number with ethyl. So this one number is having ethyl. Now the question has asked draw the Newman projection formula. So here you, as we know, we have 4 cases, both ethyl and methyl in axial, both ethyl and methyl in equatorial, or ethyl in axial, methyl in equatorial, or ethyl in equatorial, methyl in axial. There are 4 cases. So if I have to draw the most stable Newman projection formula, so I can see that in C1, this is C1, ethyl must be in equatorial, so this is your equatorial position because it is your axial position. Again, I will see C2 methyl, so this is your C2, this is your axial position and this is your equatorial position. Now these all are having hydrogen, 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 hydrogen. Now one more conclusion comes out from this conformer, why we say always that equatorial position is more stable than axial position. If you will observe this structure, you can see this front carbon atom of this part is having ethyl here and the back carbon having methyl this side. So on observing the chair conformer, we say suppose this one is having ethyl in equatorial, right, down, so this will be up, methyl in axial. We just feel that this ethyl and methyl are nearby. No, you can observe from this structure, this front having ethyl from front side towards this side and back carbon having methyl towards this side. So these are not actually towards each other, they are far away from each other. You can observe it from this Newman projection formula. Hence we say that equatorial position must occupy, this is equatorial, so equatorial position must occupy the bulkier groups. Okay, so draw most stable form of first and second now let's see, this is your tertiary butyl and this is your methyl, right? So I can say this one as 1,1 dimethyl ethyl and this is your simply methyl. Okay, so if I'll draw this conformer, so you can see here it is in wedge and it is in dash, so it is simply your transform, right? So if I will draw this one in up, then this will be in down, or this will be down, this will be up. So let's first draw the two categories, then observe which one will be more stable. Suppose I am numbering here simply. This one has 1. So CME3, if I will say down, so this must be up. 1, 2, 3. So this must be up. Okay. 1, 2, 3. As per my numbering, 1, 2, 3. This is down, this is up. So this is your trans. Or another case, I can say this in upside 1, 2, 3, and this in downside. Okay. Now I have drawn the required structure. Now let's compare which one is the most stable form. Okay. Here it is in downside, and one portion, as we know, it is equatorial. Down, up, down. If it would have been in down, then it will be equatorial. So here it is in axial part. As you see, this up, upward. This upside pointing, so up, so it is axial, right? Now, it is axial, it is equatorial. In this structure, it is pointing up and it is up, so it is axial. Here it is pointing up, but it is here down, so it is equatorial. You can see down, up, down, equatorial. Now, among these two structures, if I will say A and B, I can see that CME3 is more bulky group than CS3. So, AE and here also AE, if more bulky group occupies equatorial position, then that structure will be more stable. So I can say structure A is more stable than B. Okay, so for this compound, the required will be this structure. Understand? Okay. So now come to this structure. It is wedge, it is also wedge. So you can say it is cis form. Let's take this as one simply. CME3 down 1, 2, 3. It is also down. Or CME3 in up, and this is also in up. Now this is equatorial. This is also equatorial. Let's suppose C and this is D. So it is axial up. This is also axial. Now you can simply see both the groups are in equatorial position. Here both the groups in axial position. So both the groups in equatorial will be more stable. So among these two, for this compound, the required structure is C, as C is more stable than D. Now if I will see among these two, what is happening? This is cis and this is trans. The compound is same, molecular formula is same, structural formula is same. Only space, arrangement of atoms in space is different. So they are stereoisomer. I have drawn the 4 conformers corresponding to that particular compound. Okay, so among these 4, if I will see which one is the most stable, means I am now writing the order of stability among A, B, C, D. So I can say that order of stability among A, B, C, D will be, most stable will be stability. Most stable C, because both in equatorial. Now both axial, this will be last. D. Now among A and B, EA, EA, but more bulky in E position will be more stable. So this A, then B. Okay, so dear students, I think now you have understood each and every concept regarding how to draw Newman projection formula, how to draw the most stable conformers in case of chair conformers. Okay, so note it down. Go through it perfectly. Now let's continue with our next topic. As we have seen earlier that cyclohexane is having chair form as its most stable form. Also, when chair form is flipping, it gets inverted into inverted chair or flipped chair form. So, during this interconversion from chair form towards inverted chair form, there we find some stable conformers which have specific significance in certain cases. Okay, so let's see what happens actually during interconversion from one form to another form. So suppose see, this is your chair form. Okay, now when this chair flips, first of all what happens, this chair form, if this part comes upside, okay, if this part comes upside, what will happen? You will be making half chair. So how it will look like? It will look like this. Okay, clear? Now when this part again flips upside, then you can make it this is your boat form, this is your half chair, this is your boat, you can see here boat shaped. Now again when it flips from this side, then what will happen? First what we did, make it this side. Okay, so this comes in same plane and this is your top part, so this is your half chair. Now when this part comes upward, okay, so what happens? This is your boat conformer. Now when you take this part downside, because now you cannot make, here we started with rotating this part, it came this side, again rotated this side, now you cannot further rotate it this side, so start with this side towards this. Okay, so what will happen? Again your half chair. Okay, now again you have made half chair. Now what will happen? If you will flip this again towards this side, so you will get this is chair and this is inverted chair. Okay, so dear students, you can see from chair up to inverted chair. I earlier showed you directly from chair to inverted chair, but remember this thing, from conversion towards chair up to inverted chair, these conformers are coming chair, then half chair, then boat, then half chair, then finally inverted chair. Now again you have to understand, when this boat form is formed, see, in this boat conformation, as you know, this carbon must be V-shaped, 2 bonds this side, so 2 bonds must be this side, hydrogen and hydrogen. Again here 2 bonds must be this side and this side, hydrogen and hydrogen. So if we will consider the trans part, means this part and this part, right? So this hydrogen makes repel each other. So this repulsion is called as, this is your flag part. Okay, flag part. So this is called as flag pole repulsion. So this boat form is having flagpole repulsion. Why? Due to this trans part, this side hydrogen and this side hydrogen. So it means if the bulky groups lies at this conformer, in boat conformer, in this 1,4 position, then it will be highly unstable, right? Now what happens if this boat form in this flagpole, due to this flagpole repulsion, it is unstable? So what it makes? It makes this part twisted. So this boat form twist to twist boat form. This is your boat form. Okay. Now what this boat form will do? It will twist towards another form. So you can just see here, this part will be twisted towards you can assume this part as towards you. This is in 3 dimension. Okay, so now if I'll see what it happened, this was suppose your 1 2 3 4 5 6. Okay, so this was 1 2 3, Now this is your 4, 5 and 6. Now this is your twist boat. Okay, so what happens? First chair conformer is formed, then it will make half chair. Now you can first think as twist boat, then again twist boat, then half chair, then inverted chair. Clear? So this is the entire conversion process of chair into inverted chair. Okay dear students, so note this part completely. I hope you must have understood about this conformer of cyclohexane, interconversion from chair to inverted chair. During this interconversion from chair and inverted chair, if I'll compare this first part and this second, third, fourth, fifth, sixth, seventh. So this is your seventh part. How it is 7? First, second, then as I said half chair, then it will go into twist boat form third, then boat form is your fourth, then again twist boat is your fifth, then half chair will be 6, then finally 7. So I can understand here that chair form up to inverted chair. In chair, if any hydrogen lying in axial, in inverted chair it will go into equatorial part, right? But most important part is if it is having cis configuration, the configuration in this form inverted chair will also be cis form. Okay, so if you have drawn this part, so let's see the energy profile diagram and potential energy barrier for conversion from one part to another part. Okay. Conformational energy barrier see, the very first part I was having chair form, right? So suppose this is your chair form. Suppose I start from here. So chair form was converted into first of all half chair. Now if we will compare the stability order, this is our chair form. It is having 109 degree, 28 minute. The bond angle is perfectly okay. Axial and equatorial part, that is perfectly okay. Then we have half chair form, right? This is chair, this is half chair. Now if we will consider half chair, then we can see these 4 carbon atoms were earlier in same plane, but when this part comes upside in half chair, then 5th atom also comes in the same plane, and at the same time it will be having very high amount of strain. Means 2 are already in eclipsed form in same part, and again 2 have come. So overall it is the most unstable part of this chair conformer interconversion. Okay, then we have this part. Okay, then we have boat. So we have this first, second, third and fourth. If I'll say fifth inverted chair, so that was almost same only. So this was this side, this will be this side. It was long, so it will be short. Okay, so this is your simply fifth. So first of all, we started with this one as your chair. It converted into half chair. So this I am simply saying half chair or second. Then half chair converted into twist boat. Okay. Comparing the stability among 1, 2, 3, 4. So we can say most stable part will be stability 1. Then here comes 3 twist boat. Then here comes 4. Then here comes 2. Why this happens? This is most stable. This boat was having flagpole repulsion. To minimize the repulsion, what we did, we made twist boat. So this will be more stable than this, and finally this, because it is having maximum strain in this ring, in this conformer. Okay, so now let's complete. Chair converted into half chair, then it converted into twist boat. but it must be having energy more than chair. So here we got twist boat. Then we get boat conformer, right? Again we get twist boat. Then from twist boat again we get half chair. And finally we get chair. So from interconversion I can again mention same. This was your 1, half chair 2, this was your 3, 4, 5. You can match it with the earlier diagram, 6, and this is your 7. So this is chair, half chair, then this is your twist boat, this is your boat, then this is again twist boat, then this is your half chair, and this is your chair, but better to say inverted chair. Inverted chair. Okay, so this is the complete energy profile diagram. Now let's see the energy barrier on interconversion from one form to another form. Okay, so with respect to chair form, if I'll see twist boat, this energy barrier is approximately 23 kilojoule per mole. Okay, from chair to twist boat it is 23 kilojoule per mole. Now if I'll see with respect to chair and boat conformer, this is approximately 30 kilojoule per mole. Okay, now if I'll see with respect to chair and half chair, it is approximately 45 kilojoule per mole. Okay, so dear students, I think you must note these values and remember it. I'm just telling an approximate values. Okay, 23 kilojoule per mole with respect to chair and second most stable twist boat. Now again, suppose you are asked a question that what will be the energy barrier with respect to twist boat and boat, then what you have to do? This part, just calculate it. This overall is 30 and this part is 23. So this part must be what? 30 minus 23. This must be 7 kilojoule per mole. So in that way, you have to make interconversion on these data and give the answer as per requirement. Okay, so draw it first of all. Now we have completed with different form of chair conformers during interconversion, boat, twist boat and half chair. Now let's see gauge effect. See students, it is one of the very important topic, as if I see the last 20 years previous year questions, then many times this topic has been asked in JEE as well as NEET examination. So understand it very carefully. Okay, now gauge effect, what is it? So sometimes what happens, instead of anti-form, gauge form is more stable, right? As we have earlier seen, in place of staggered, fully staggered or anti, partially staggered or gauge, eclipsed, partially eclipsed or fully eclipsed. Among these four conformers, we have seen anti-form is the most stable because it is having least strain, both least torsional strain and van der Waals strain. Then comes your gauge effect, gauge. Then comes partially eclipsed, then comes fully eclipsed. But in some cases, it has been observed that gauge form is even more stable than anti-form. Okay, so let's see how. Case 1 is hydrogen bonding. Now if I'll tell about hydrogen bonding, so this topic I have already discussed you in terms of one question. Okay, what happens if you draw CH2, CH2, OH, OH, as you know it is ethane 1,2-diol, and we have earlier drawn this structure also, that more stable part will be gauge part. Okay, here most stable form was gauge form, then your anti-form. Why? Due to this intramolecular intramolecular hydrogen bonding in gauge becomes more stable than antiform, right? So this is the case. Now I am giving you a very short note on this thing. Suppose you are having CH2, OH, CH2, and this group is, suppose you are calling any group Z. Okay, so if I say Z equals to NH2, or if I say OH, if I say C double bond O and H, if I say C double bond O, OH, if I say O, CH3, in all these cases, gauge form will be more stable than antiform. Why? This OH is having oxygen and this Z is having a group which is more electronegative. Like here, you can see nitrogen, oxygen, this C double bond O oxygen, this C double bond O oxygen, or this OCH3 oxygen, right? So these atoms can form hydrogen bonding. Again, if I'll say, if you have fluorine or chlorine, in both the cases, I have discussed these two examples. In case of fluorine or chlorine, due to lone pair and hydrogen here, it goes intramolecular hydrogen bonding. Yes, chlorine is a special case here. Chlorine is having intramolecular hydrogen bonding. Okay, so remember this part. Gauge is more stable than anti in all cases. Clear? Okay, so this was your case 1 of gauge effect. Clear? So let's come to next part. Let's take with an example. If we'll think simply, we may come across a thought that here among these two, this is your antiform and this is your gauge form, right? So among anti and gauge form, if I'll see, gauge form is less stable than antiform generally, if you will think, but here it has been observed that gauge form is more stable. Observed, gauge form is more stable. Now, how this gauge form can be more stable? Let's understand it in detail. Okay, gauge form more stable than antiform. How it happens? Let's observe. See, if this fluorine atom of this front carbon is having this fluorine, having lone pair of electron as well. Okay, so if this fluorine, hydrogen, 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 in this antiform, let's draw these are on same side, right? Okay, so it is your what? Eclipsed form. Now if I draw its gauge form, suppose H, H, F, H, H, F. Okay, now you try to understand. When we draw, this is your fully staggered, right? Now this is your staggered. In this staggered form, if I will see this Ca bond is having electron pair here, with respect to this Ca bond, this CH bond is this side. Okay, now this Ca bond is this side, so this Ca bond must be having some, according to MOT I am explaining, right? As per VBT we cannot explain this thing. So most of the books, what they says, they simply says gauge is more stable than antiform. But I am explaining you in short what is the possible reason for this case. In antiform what happens, this CA bond is having your anti-bonding orbital this side. So here you are having in this side, this back side of this CA bond is having your anti-bonding molecular orbital, sigma star. Okay, so this sigma star and this CA bond can make, there is a possibility that it can make some sort of electron sharing. But now what happens, as this fluorine is most electronegative and this CA bond, this fluorine is attracting electron pair towards itself, so in anti such possibility is not available. But now this CF, H, right, this front part, okay, and now this back part, F, H. Now I have drawn, this is gauge form, right? So this C fluorine, carbon fluorine bond is having some sort of anti-bonding orbital this side, and this CH bond, the electron pair may partially shift towards this side. So that may be a possibility due to which gauge form here is observed as more stable than antiform. Okay, so this is simply your gauge effect, which says that in case of fluorine, gauge form is more stable than antiform. Okay, now if I'll say about eclipsed, then simply partially eclipsed is more stable than fully eclipsed. So the order in this case will be in 1,2-difluoroethane. Remember this question, in 1,2-difluoroethane, gauge form, then antiform, then partially eclipsed, then fully eclipsed. Okay, in anti it is not possible. In gauge it is possible that this CF bond is having some anti-bonding MO, where this CA bond is partially transferring its electron this side. So due to such stabilizing effect, if there is some sort of sharing of electrons, then there must be decrease in energy, and if energy decreases, stability increases. So due to this reason, gauge form is more stable. Now what happens if this fluorine is replaced by chlorine, bromine or iodine? So understand the remaining cases. CH2, F. In case of fluorine, gauge is most stable, but if I say CH2, X, here X equals to Cl, Br or I, anti will only be more stable than gauge form, because such possibility is observed only in case of carbon fluorine bond. Okay, so just remember this example only. In 1,2-difluoroethane, gauge form is more stable. In remaining these cases, antiform will be most stable than gauge form, right? So this was one of the part. Now let's understand few more cases which relates to this gauge effect. First, draw conformers of CH3NH2 CH3OH. Okay, so here with respect to carbon and nitrogen, you are rotating this bond, free rotation with respect to carbon nitrogen. So let's first learn how to draw this structure. So if I'll say this as back carbon and front part as nitrogen. Okay, so this is your lone pair, this is your hydrogen. Okay, back side this carbon is having hydrogen and hydrogen. Okay, this is one way of drawing this structure, or sometimes you may come across the structure like this. This nitrogen is having lone pair like this, H, and this carbon is having H. Okay, so this is your methenamine. Okay, so this is the structure. Front atom nitrogen having 2 hydrogen, backside carbon having 3 hydrogen. Similarly, if I will draw this structure, then suppose this is back carbon atom and this is oxygen. So one lone pair this side, one lone pair this side, and this hydrogen this side. Here CH3. So H, H, H. As we know, staggered form will be only stable here, right? Or you may simply draw this structure as lone pair, H, and this carbon is having H, H, H. Now, here there was no need of as such Gauge effect, right? I just made you to understand how to draw in case of lone pair. Now understand some special examples. Draw most stable conformers of first CH3 CH CH3 OH across this carbon oxygen bond. Okay, this is the first thing. Now let's draw this oxygen and this back carbon. This oxygen is having two lone pair. Simply draw lone pair and hydrogen. Now this carbon is having one hydrogen and two methyl. First you may come across this thought that let's place hydrogen among these two, right? And this methyl this side, this methyl this side. Or you may think another possibility of lone pair, hydrogen. One methyl here, and one hydrogen here. Now let's observe these two structures one by one. In this case, two lone pair, and in between that you are having hydrogen atom. This methyl and this lone pair, this methyl and this lone pair, right? Methyl hydrogen. I am just mentioning you the stain part. Now in this structure what happens? Both lone pairs, and in between the lone pair you have placed the bulky group. Again methyl lone pair, similarly methyl lone pair, methyl hydrogen, hydrogen. Now the question is, which one is more stable? So here students understand, Gauge effect says that structure number 2 is more stable than 1. Second will be more stable than first. Now you may come across, sir, how? So just understand, as per Gauge effect, the lone pair and the bulky group, if occupies Gauge position, then that conformer will be most stable form. Okay, so here this lone pair and this bulky group in Gauge form will be more stable. So second is more stable than first. Clear? Okay, so let's see another example of CH3 CH ET N H ET across carbon nitrogen bond. Okay, I think everyone must have drawn this structure. Nitrogen, and backside is your, see, this nitrogen is having one lone pair, hydrogen and ethyl. This carbon is having hydrogen, ethyl and methyl. Okay, so these three positions we have. Now you have to think which is the most stable case. As we know from Gauge effect, bulkiest group must be near Gauge to lone pair. So if I'll place this ethyl here, lone pair and ethyl, that is okay, but here also ethyl, so this is having maximum stain. Now if I'll place ethyl here, then lone pair and ethyl and hydrogen, so that is okay. So let's place ethyl here. Now again the question comes, where to place methyl? Methyl here and lone pair, that is okay, but methyl-ethyl repulsion. Again if I place methyl here, so methyl hydrogen repulsion as well as methyl-ethyl repulsion. So ethyl-methyl is common in both places, but lone pair and methyl, so that will be stability gaining part. So methyl here and hydrogen here. This is the most stable conformer for this case. Okay, so note it down.